something is amiss in our comprehension of the universe. Cosmology by all accounts is heading for a confrontation on one of its most fundamental inquiries. How fast is the universe expanding for more than a decade? Two kinds of estimations have been in conflict. Observations of the current universe commonly find the rate of expansion, called the Hubble constant, to be around 9% quicker than predictions based on early universe data. Analysts hope that the James Webb, the most advanced telescope ever constructed, would help settle the question unequivocally. However, a consensus has so far failed to appear. Rather, the preeminent observatory has solidified the error with amazingly exact novel observations that threaten to overturn the standard model of cosmology. The new physics expected to change or even replace the 40-year-old theory is now a subject of debate, an astonishing and intriguing possibility that there's something we don't understand about the universe. Join us as we dive deep into how new ultra-deep images from James Webb have just confirmed that there is something genuinely amiss with our interpretation of the universe. Our universe began with a bang. The Big Bang, energy, mass, and space flashed into reality all within a passing moment. Then the youthful universe was formed, a growing, swirling plasma stock of matter and antimatter particles that jumped into reality only to destroy each other upon contact. Left to their own devices, the matter and antimatter inside this plasma would have consumed one another completely. However, scientists believe some obscure imbalance allowed more matter than antimatter to be created, saving the universe from rapid implosion. Gravity packed the plasma pockets, crushing and warming the matter so that sound waves, traveling just over half the speed of light, called baryon acoustic oscillations, undulated across their surface. In the meantime, the high energy density of the early universe's crowded content expanded spacetime, pulling a small part of this securely from the fray. As the universe expanded like an inflatable, as the standard story goes, normal matter, which interacts with light, hardened around clumps of invisible dark matter to form the first galaxies, connected together by an immense cosmic web. At first, as the universe's substance spread out, its energy density and thus its expansion rate diminished. However, about 5 billion years ago, galaxies began to retreat again at an ever-increasing rate. The reason was another invisible and puzzling substance known as dark energy. The simplest and most famous explanation for dark energy is that it is a cosmological constant and inflationary energy that is the same everywhere and at every moment, woven into the expanding fabric of spacetime. Einstein named it lambda in his theory of general relativity. As our universe expanded, its general matter density dropped while the dark energy density remained the same, progressively making dark energy the greatest contributor to its overall expansion. Included in the energy densities of normal matter, dark matter, dark energy, and light are the upper speed limits of the universe's expansion. They are also key ingredients in the lambda cold dark matter lambda CDM model of cosmology, which guides the expansion of the universe and predicts its end. When matter is spread that far, it encounters a heat death known as the Big Freeze. Many of the model's predictions have been shown to be extremely accurate, yet here's where the problems begin. Despite much searching, cosmologists have no clue what dark matter or dark energy actually are. As Ofer Lav, a professor of astronomy at University College London involved in galaxy surveys of dark energy, said most people agree that the universe's current makeup is 5% normal matter, 25.5% cold dark matter, and 70% dark energy. The embarrassing reality is we don't know the last two. However, an even greater challenge to the lambda CDM model has emerged. Depending on which method astrophysicists use, the universe appears to be expanding at different rates. A discrepancy known as the Hubble tension methods that account for the early universe show it expanding much faster than the lambda CDM model predicts. These methods have been tested and confirmed by numerous observations. For instance, Nobel Prize-winning astrophysicist Adam Ree, who led the team that made the new James Webb estimate, said the only reason I can understand for them to differ is that the model we have between them is maybe missing something. Measuring the universe versus expansion takes a bit more than a radar gun. The main method to measure this expansion looks at the so-called cosmic microwave background, CMBB, a remnant of the universe's first light created only 380,000 years after the Big Bang, the imprint should be visible across the whole sky, and it was designed to find the Hubble constant with less than 1% uncertainty by the European Space Agency's Planck satellite between 2009 and 2013. In this baby picture of the universe is predominantly uniform but hotter and colder patches, where matter is more or less dense, reveal where baryon acoustic oscillations made it clump together. As the universe expanded outward, this soap bubble structure swelled into the large cosmic web, a network of strands along whose intersections galaxies would form. By studying these waves with the Planck satellite, cosmologists gather the amounts of normal matter, dark matter, and values for the cosmological constant, or dark energy. This was plugged into the standard model, which yielded a Hubble constant of about 67 kilometers per second per megapark. MAP park is 3.26 million light-years. Let's pause on this number for a moment. If a galaxy is 1 megapark away from us, that means it will recede from us and we from it at 67 kilometers per second. At 20 megaparsecs, this recession grows to 1,340 kilometers per second and continues to increase dramatically from there. If a galaxy is more than 4,175 megaparsecs away, it will recede from us faster than the speed of light. A second method to find this expansion rate uses pulsating stars, called CADs, dying stars with helium gas outer layers that expand and contract as they absorb and emit radiation, making them occasionally glow like distant signal lights. In 1912, astronomer Henrietta Swan Leavitt discovered that the brighter a skate was, the slower it would pulse, allowing astronomers to measure a star's absolute brightness and thus its distance. It was a milestone discovery that turned science into plentiful standard candles for measuring the universe's large-scale structure. By combining observations of pulsating sides, astronomers can build distance ladders, each step taking them further back into the past. To build a distance ladder, astronomers start by selecting nearby seeds and cross-checking their distances based on pulsating light with what's found by geometry. The next steps are added using side Z, weighing nearly 50 billion times the mass of the Sun, to the 4.3 million solar mass behemoth known as Sagittarius A*, in the center of our Milky Way. But how they got there is one of the great unresolved problems of cosmology. We know that a stellar black hole forms in a super explosion where the core of a star collapses, but no one knows how a super massive black hole forms. Over the course of most of cosmic history, the centers of galaxies have been places where a great deal of matter is concentrated in a small volume. It could be the case that very large black holes form in a dense star cluster made up of stellar black holes which repeatedly merge with one another. Indirect evidence for this comes from a merger between two black holes detected by gravitational waves, where one black hole was too large to be a remnant of a stellar explosion. Thus it may have started in an earlier merger. An alternative way to form a supermassive black hole is through the direct collapse of a massive cloud of gas. It may be that supermassive black holes form from a combination of cloud collapse and black hole mergers. It's also possible that very large black holes formed in the Big Bang itself. This would answer the cosmic chicken and egg problem: which came first, galaxies or supermassive black holes, rather than galaxies forming first and then giving birth to these monsters. It may be the case that supermassive black holes formed first and provided the seeds around which galaxies of stars formed. Despite their masses, even the largest supermassive black holes are not larger than the nearby planetary group, but they project their power across billions of light-years by means of oppositely directed extremely fast jets of matter. Where these jets are fast in the inner regions of a galaxy, they drive away gas. NEXT distinguish star formation. Where they slow down in the outer regions, they compress gas and trigger star formation. In fact, powerful jets from the largest black holes seem to control most of the stars that form, with a preference for smaller cool stars like our Sun. So who knows, it may be the case that we can thank Sagittarius A** for our Sun, without which you probably wouldn't be here now. Dark matter gives out no light, or too little light for us to detect. We know it exists because we can see the effects of its gravity on visible stars and galaxies. For instance, the Milky Way could never have pulled in enough matter to make its stars in the 13.8 billion years since the Big Bang, without there being a lot of unseen matter whose extra gravity sped things up. The European Space Agency's Planck satellite found that dark matter accounts for 26.8% of the universe's mass energy compared to the 4.5% of ordinary bionic matter. It thus outweighs the visible stars and galaxy by a factor of around 64 years. The favored candidates for dark matter particles have been weakly interacting massive particles WIMPs. However, although these particles fit the bill, they failed to appear in experiments at the Large Hadron Collider near Geneva in Switzerland. A candidate gaining favor is the superlight Ocean, a theoretical subatomic particle. Another idea is that dark matter remains as early-stage black holes left over from the Big. Mysteriously, no Earth-based experiment has found any proof of dark matter. Despite decades of searching, it's possible that it's not our theory of matter that needs adjustment, but our theory of gravity, or perhaps dark matter is not a fluid made of a single particle, but something more complex like the ordinary matter we see around us. Maybe the universe is full of dark stars, dark planets, and even dark life.